In this lesson, we look at the dynamic characteristics of non-return valves. You might call them check valves or reflux valves. This lesson is delivered in 3 parts. Wait up. What's going on here? I know I'm talking about you, but you come out later, not now. So off you go. Come back later when I need you. Sorry about that. Animated graphics with a mind of their own, or an assistant with a sense of humour. Where was I? The lesson on non-return valves has 3 parts, presented in 3 separate videos. Part 1 is the video you are now watching and is about knowing when you need to evaluate the transient effects caused by slow closing non-return valves and when you do not need to know. The Part 2 video looks at the transient effects caused by slow closing non-return valves. Part 3 takes a qualitative look at the variety of non-return valve types and how they compare in terms of their ability to close rapidly before the water column reverses its flow direction. That's when I will need those graphics to reappear. Much later in the whole course, the case study will show you how to use the WATHAM software to evaluate the reverse velocity that a water system can generate through a slow closing non-return valve. That later case study also demonstrates how to use WATHAM to analyse the consequences of a non-return valve slamming shut against a significant reverse velocity. So let's jump into part 1. When is it appropriate to evaluate the consequences of a non-return valve's closure time, and when is it not necessary? All non-return valves take a finite time to close. The time delay between the fluid reaching zero velocity and the non-return valve's gate closing, I'm calling the valve's closure time. The WATHAM software allows users to specify a closure time value for each non-return valve. So for a transient analysis software user, the question becomes, when can I safely assume an ideal non-return valve with a closure time of 0 seconds? And when do I need to give the non-return valve a realistic non-zero value for its closure time? The answer revolves around the focus of the current stage of an engineering project. Is the project currently focused on defining the size of the overall system and its capacity? Or has the project progressed to a later stage when the focus is on detailed design of an individual asset within the system? When you are analysing the transient performance and surge protection for a whole water system, it is not necessary to simulate the surge effects of slow closing non-return valves. In system-wide transient analysis, it is valid to assume each non-return valve is perfect and has a 0-second closure time. An additional justification for initially assuming perfect non-return valves is that until the overall system surge protection is analysed, sized and located, the overall system is not yet defined. For example, until it is known whether pressure vessels are needed on the delivery side of a pump station and the amount of energy to be stored in their compressed air volume, the potential for the system to generate reverse velocities through the pump station's non-return valves is not yet defined. Even during system definition, to safely apply a 0-second non-return valve closure time, 2 assumptions need to be true. 1. The surge effects of non-return valve slamming are local, for example confined within the pump station. And 2. Surge amplitudes generated by slamming non-return valves are relatively minor in the context of the overall system surge amplitudes. These assumptions generally turn out to be true in many projects. At a later stage of each pumping project, when the design team is selecting the mechanical equipment within a pump station, it becomes appropriate to do a series of transient simulations using realistic non-return valve closure times. At that stage of the project, Transient simulations should be set up to examine the magnitude of reverse velocity the system can generate and the consequences of the non-return valves slamming shut.